In this video, we're going to take a look at Newton's third law, which is about action-reaction forces. You've probably heard the saying, for every action, there is an equal and opposite reaction. In physics, we mean that every force has an equal and opposite force. The basic idea is this. If you were to attach a rope to a crate and pull the crate, you could ask yourself the question, do you pull on the crate? Well, yes. That's what you're trying to do. You're applying attention to the crate. But does the crate pull on you? In other words, do you feel pull on the rope? Do you feel something on the rope on your hand? Certainly you also feel that. And Newton's third law tells us that these two forces, the force of tension that the crate is putting on you and the force of tension that you are putting on the crate, are equal in magnitude, the same amount of force. This is what an action-reaction pair is about. They're always opposite in direction. The crate is pulling backwards on you. You're pulling forwards on the crate. They're acting on these two different objects, on the crate, on you. And they're always the same kind of force. In this case, the rope provides a tension both on you and on the crate. For example, gravitational force and normal force could never be a third law pair because they are different kinds of forces. So when we're thinking about the interactions between two objects, which is where the third law really gets into it, we're going to go through a series of questions here to help you think about what is going on with Newton's laws. You're going to be asked to answer each question before moving forward. So here is our first question. A block is being pushed with a constant frictional force acting on it, and it moves at a constant velocity. We want to compare various forces. So the first question is, compare the magnitude of the force of the hand on the block, force HB, force hand on block, to the force of the block on the hand. And so at this point, you'll answer the question before we move on. So in this case, Newton's third law says these two forces have to be equal. Well, what about in a different situation? What if the block is still being pushed at a constant velocity? Compare the magnitude of the force on of the hand on the block to the force of friction. Well, in this case, the force of the hand on the block and the force of friction have to be equal to each other because it's moving at a constant velocity. Same scenario, constant velocity. The hand is still pushing on the block, but what is the net force on the block? Well, because it is a constant velocity, the net force has to be zero. Now we're pushing the block so it speeds up. Compare the magnitude of the force of the hand on the block to the force of the block on the hand. Again, Newton's third law tells us that they should be equal. Now if we compare the force of the hand on the block to the force of friction, if it's speeding up. In this case, because it is speeding up, the force of the hand on the block must be bigger than the force of friction. Same scenario, being pushed so it speeds up. What's the magnitude of the net force on the block? The net force on the block has to be the applied force, the hand on the block, minus the frictional force. And so you'll notice that there's this pattern of these questions. The first question was the third law question. The second question was a question about relative size of the forces on one object, really a first-second law question. And this last one is a net force, or Newton's second law question. So we're really trying to understand where each law applies. Next question. A block is pushed so that it slows down. So you get it moving, but as you're pushing it, it's slowing down. How does the force of the hand on the block compare to the force of the block on the hand? Again, this is a third law situation that we're talking about. Two different objects. We're saying, see, they should be equal to each other. Same scenario, push so it slows down. How does the force of the hand on the block compare to the force of friction? In this case, the frictional force must be bigger in order for it to slow down. Finally, for this scenario, the block is pushed so it slows down. What is the magnitude of the net force on the block? In this case, it's still the force of the hand on the block minus the force of friction. Friction just happens to be bigger, so we get a negative acceleration. What if we push this object push two hands together such that they move in the positive direction. Is the force of persons A on B greater than, less than, or equal to the force of person B on A? Again, a third law situation. What if we did it in the opposite direction? We have now motion in the negative direction. Again, this is a third law situation we're talking about. The forces should be the same. So now we get to some things we can actually test, right? You might be saying, I don't know, this may be true, but how can we be sure? So what I have done is I've recorded some videos, and you can see here's one of them, of two carts, carts A and B, and one of the carts is up against a wall, and we're going to be able to watch this video of the carts being pushed against each other that I do there, and then I let go, right? Cart being pushed up against the wall, just like it describes in the scenario. And so what I want to know is, will the force of A on B be greater than, less than, or equal to the force of B on A if A is pushing up against B up against a wall? All right. We know from the third law that the two forces should be the same, but can we see that happen? So I've synced up the video here so we can actually watch what happens when the video goes through and plays what's happening, and we get the graph of the force. So let's watch. And what we get is I start out pushing pretty hard, and then I let up, and then I get push hard again. But in all of these cases, as we go, we get this mirror image. The force that the greenish blue car feels is the same as the force that the yellowish car feels, just in opposite directions. Our next question says, what if I push the cars towards each other, kind of like a head-on collision? Will the force of A on B be greater than, less than, or equal to the force of B on A? Again, Newton's third law says they should be the same, but let's check. Same basic idea. I've got a video where I'm pushing the cars towards each other a couple of different times, colliding them, and we can see what this looks like. Right, in those collisions, we get those results. Equal and opposite forces, no matter what we do. For this question, we're now no longer pushing two identical mass objects. We're now pushing a truck. And to do this, I've added some weights to the cart. You can see them in this video frame, that the cart now has some weights on it. So it's a little bit heavier. So will the force of the truck on the car be greater than, less than, or equal to the force of the car on the truck? Newton's third law again says that they should be equal. So we can go ahead and see that happen. Regardless of what I do, if I push the heavy into the light, I get this mirror image. So that's exactly what we said before. So this time we're going to do the opposite. We're going to push the light car towards the huge truck. So again, the same question, will the force of the truck on the car be greater than, less than, or equal to the force of the car on the truck? Newton's third law once again tells us they should be equal. So we can check that out. Even if the one doing the colliding is the light one, we still get this nice mirror image, equal and opposite forces. We can do a little bit more with this by observing that it doesn't really matter what we do with the motion. I've called this video All the Motion. But if we watch what happens, I can move them around, accelerate them, kind of do whatever I want, and I get this nice mirror image, equal and opposite forces for whatever I do. And this leads us to a couple of other kind of summary questions. Can an object at rest exert a force? Yes, of course it can. We've seen that happen. Another question. If you push the car into the truck, is it possible to push the car fast enough so the magnitude of the force of the car on the truck is greater than the magnitude of the force of the truck on the car? According to everything we know, it should be impossible. B. So, in summary, every force has a reaction force, and those forces are always equal in magnitude, opposite in direction, acting on a different object, and always the same kind of force. This does lead to something that you'll discuss in class with your classmates and your teacher. Newton's third law is true, that for every force there's an equal and opposite force. How can any object ever accelerate? Interesting.